Okay, sorry for cutting earlier. So in this video, let's just have a proof of the open mapping theorem. So what does the open mapping theorem says? The open mapping theorem says that if T is a bounded operator from X to Y and T of T is surjective, then T is an open mapping and this is if and only if the set, this is if and only if there exists an R positive such that the ball of radius R of Y is contained in T of B1x. Okay, so this is the image. This is all the T of X such that X is in B1x. Okay, and so this if and only if I'm not going to show, but the idea is that we can just use linearity. So if we have, so 0 is a point that is in T of B1 of X because 0 of Y is in T B1 of X because T of 0x is equal to 0y. Okay, so in particular, so if you have the point 0 of y, which is in B1 of x, so then you can actually just translate this around. Okay, so, and the fact that BR of y is in T of B1 of x, then you can just use linearity to multiply here. If we have T of B, let's say Lx, here you will have BRLY. Okay, so you can actually just start playing with all of this, and then showing that T is an open mapping is equivalent to just showing this property. Okay, because everything is you can always translate everything around 0. So then if you have some point, some mapping T of x naught, which is equal to y naught, then you can treat this as 0 and then see that there is a little ball around this point. Okay, so the proof of this, we're going to use the Baire category theorem. And let's see how we use this. So T is surjective. T is surjective, then this implies that X is equal to the union of K equals to 1 up to infinity of K times B1 of X. Okay, so this is the ball of radius K around 0, and we are going to take K, which is going to go into 1 to infinity. So then, what is our hypothesis? Our hypothesis, this is by hypothesis, that T is surjective, is Y is equal to the union from K equals to 1 up to infinity of T of K B1 X. Okay? Sorry, and this would be the T is outside. But now the union of these images, we can take it outside. So this is just the union of K equals to 1 up to infinity of T of K times B1 of X. So in particular, what we can say is that Y is also equal to the union. Try to get this camera to work well. So this is also equal to the union of k equals to 1 up to infinity of tk b1 x closure. Okay, so this is the closure. So the closure contains the set, so if we take the union of the closures, this has to be contained in there. But now here is where we are going to use Baire category theorem. So Baire category theorem says that a complete metric space is not a countable union of closed sets with empty interior. Okay, so here we have a countable union of closed sets. Okay, so these are closed for every k. Okay, so therefore there exists a k star such that the interior tk b1x star closure interior is different from the empty set. Okay, so this is what Baire category theorem tells us, that there exists one k star, and we'll show, of course, that by linearity, if you can do it for one, you should be able to do it for all of them. In particular, there is one k star in which this is non-empty. So what does this mean? So this means that there exists a y star, and so there exists a y star in y and r star positive such that the ball around y star of radius r star, and this is a ball in y, is contained in tk star b1x closure. Okay, so let's just put the closure on top. Okay, but now let's take a y in the ball of radius r star of y. Then what do we have? So this property here is telling me that y star, comma, and y star plus y is contained in the image of k star up times b1 x closure. So in particular, now we can take the difference of these two guys, and this is going to be in the difference of the closures. Okay, so now we do a little algebra. So y is equal to y star plus y minus y. Okay, but these guys are in tk star b1x closure, so this is in the closure minus another element of the closure. Okay, but now we use linearity. So in particular, we can take the closure of the difference. So the difference of the sets is just taking all of the possible differences of all the elements in this set and in this set. So in particular, by linearity, this is contained by linearity. This has to be contained in the closure of T of 2k star B1x. Okay, so if you have one element which is in the closure of this, and you have subtract an element which is also in the closure of this, then if you take the maximum distance between the images of the points in X can only be 2k B1x. Okay, so you will always find, so how do I do this? So let's say that we have C1 here, C1 and C2 here. So then C1, this implies that there exists X1, X2, such that T of X1 is equal to Z1 and T of X2 is equal to Z2. Okay, and this is in K star B1 of X, and this is in K star B1 of X. But in particular, if we take Z2 minus Z1, this is equal to T of X1 T of X1 minus X2, then by linearities this is T of applied to the difference, but this guy will always be in 2k star B1 of X, and this is just by taking the triangle inequality. Okay, so this is triangle inequality. The norm of the difference will be less or equal than the sum of the norms, and the norms are both less or equal than k star, so then this guy will have a norm less than 2 times k star. Okay, so then this shows that for every y in B star, in B R star, we are in the closure of 2k star B1x. Okay, so then what are we saying is that then R star B1 of y is contained in T 2 times k star times B1 of x closure. But now we can apply linearity, because we took something that is in the ball of radius R star of y, which we just wrote an R star B1 of y, but now we can just use linearity in the similar way that we use here by dividing by R star to get that this implies that B1y is contained in T2k star R star divided by R star times B1 of x closure. Okay, and so for simplicity, we are going to call this L star. It's just a number that we know that exists, positive number that we know that exists. And so in particular, so the same way, so this is by linearity. We have this, and in general, we can use the linearity to say that B, and I'm running out of letters, but let's call it B T of y. So this is the ball of radius T. Positive. This is going to be contained in the closure of little t times L star. This is going to be contained. So this is t times B1. B of radius T should be contained in T times L star B1 of x closure. Okay, so this is using the linearity of this guy. So let's rewrite this in a different way. Okay, so what we want to show is that we want to show something a little bit different, but let's try to show let's see what this means. What does this mean? So what we're saying is every element in BTY is contained in the closure of TTL star B1X modulus. Okay? So then what does this imply? This implies that for every Y in Y and for every epsilon positive, there exists an XY in the, so there exists an XY such that the norm of XY is less or equal than, so if Y is in the ball of radius T, then X of Y is going to be in the ball of radius TL star. So in particular, the norm of XY will be less or equal than norm of Y times L star. Well, so there exists an XY epsilon, so XY epsilon less than the norm of Y L star, such that this and Y minus A X Y, this is the operator T times X Y epsilon is less than epsilon. Okay, so here what I'm using is the notion of closure. If every element here is in the closure of this thing, it means that for every element within this ball, I can find an element in this ball which is arbitrarily closed. Okay, so the main point is to translate this inclusion into this inequality, where this L star here is what's coming in there. Okay, so just to not complicate things a little bit, so what we wanted to show in the open mapping theorem, let me see where it was. Elusive. Anyways, so what we want to show in the Baire category theorem is that there exists a little r positive such that BR of Y is contained in T1. So we want to show that this is, we want to show that there exists an R positive such that BR of Y is contained in B1. So as we said before, so again by linearity, this is if and only if, by linearity, B1 of Y is contained in T of B, T of 1 over R B1. So showing that there exists R positive such that BRY is contained on T1 is the same that saying by linearity that B1 of Y is contained in T1 over R times B1, which again is the same that saying that there exists a little s positive such that B1 of Y is contained in T of S B1. Okay, So what we're going to be showing is this last property here. Okay, and the way that we're going to do it is by using this little property here. In particular, what we are going to show is that if this is the L star, we are going to show that B1 of y, we will show that B1 y is contained in T2L star B1 of x. Okay, so just to remind you a bit, this is fairly similar to what we were doing in the corollary of the open mapping theorem. So basically, this thing here is equivalent. This is sort of equivalent to T inverse being bounded. Okay, and this is just an observation. Of course, we are missing the injectivity, but this property is equivalent to the pre-image being bounded. Okay, so how do we show this thing? So for every y in B1, we are going to construct xy, which is in B2L star of x, such that y is equal to T of xy. Okay, so again, this is just another way of rewriting the same thing. So the thing that we're going to use is property, let's call it property 1. Okay, so pick epsilon equals to pick epsilon equals to 1/2. Then by star there exists, and let's call it x1, such that the norm of x1 is less or equal than the norm of y, which is less than 1, times L star, and y minus T of x1 is less than 1/2. Okay, and now we are going to call this y1. Okay, so now we have to do this thing iteratively, and so we pick epsilon equals to 1/2 squared. So then by star there exists x2 such that the norm of x2 is less or equal than the norm of y1 times, so this y1 is in y, so I can actually keep doing this. I can keep, so this is for every y, so I can do it everywhere. This is less than the norm of y1 times L star, and y1 minus T of x2 is less than 1/2 squared. Okay, but this implies that y minus T of x1 plus x2 is less than 1/2 squared. Okay, so now we construct xn inductively, we construct xn inductively such that the norm of xn is less or equal. So again, this is what I would be calling y2. So we construct xn yn inductively such that the norm of xn is less or equal than the norm of yn times L star, which is less or equal than 1, so xn plus 1. Yeah, okay, so the point is we don't need to even define the yn, so this is less or equal than L star times 2 to the n minus 1, because here you had to put yn minus 1, and y minus t of x1 plus x2 plus all the way up to xn in norm is less than 1 over 2 to the n. Then what we can show is that the sum from n equals to 1 up to k of xn is a Cauchy sequence in x. Therefore, there exists a limit xy. Now, the norm of xy is less or equal, so it's less or equal than the norm of the sum of the norms of xn, n equals to 1 up to infinity, which is less than 2L star. So therefore, and y is equal to t of xy. Okay, this is by this property here, and this other part is by this property here. Okay, so in particularly, we have shown that for every y in B1 of y, there exists and x of y in 2L star B1 of x such that y is equal to t of xy. Okay, and this shows the desired open mapping property. Okay, so the open mapping has a bunch of has a few different corollaries. One of them, which could be seen in other way, is the closed graph theorem. So theorem closed so let's see if we can do the closed graph theorem. So the closed graph theorem says that t from x to y linear is bounded if and only if the graph of t which is equal to graph of t, which is all x comma tx, such that x is in x, which is contained in the product space x cross y, is closed. Okay, so linear mapping is bounded if and only if the graph of t, g of t, is closed. Okay, so the proof. So this implication is clear by continuity. Okay, so let's see if I can remember the proof of the other way around. So let's go the other way around. So what is the other way around? So assume g of t is closed. So assume g of t is closed. Then, then g of t is a linear space which is closed. So these guys x and y are Banach, which is closed in x cross y, which is also a Banach space. Then g of t is a Banach space. Okay, so what maybe it's not completely clear at the beginning, but the idea is that if you take any, if you multiply by lambda using the linearity of t, then you can see that g of t contains lambda times lambda x lambda tx, because this is just the image of t lambda x. Okay, and so the part that this is closed, this implies that g of t is a Banach space. Okay, so now we want to use the open mapping theorem or its corollary. So what we're going to do is we're going to consider, put something under this. So we're going to consider the map, the projection map, which is R, that is going from g of t onto x, given by R of x dx is equal to x for every x. Okay, so every point in the graph, which is x dx, I just project it onto its first coordinate. Okay, so this is projection . So what are the properties of R? So R R is bijective. Just because you have a projection onto a graph, and the projection onto a graph because t is a function, because t is a function with full domain. Okay. Moreover, R is bounded. So how do we show that R is bounded? So now we take the norm of R of x dx, and this is the norm of x. This is just the norm of x, but this is less or equal than the norm of x times plus the norm of t of x, which is equal to the norm of x comma tx with respect to the product topology, which is also with respect to the graph of t. Okay, so in particular we have R bijective R bijective unbounded, which then implies by the corollary that there exists S that is going from x to g of t, which is the inverse. There exists x to g of t bounded, which is a linear bounded mapping, which is the inverse of R. Okay, so what do we know is that R of, so then S of x is equal to x tx for every x. So in particular, by using the fact that this is bounded, using that S is bounded, then the norm of x dx is less or equal than the norm of S times x. But this thing here, this is the norm in the product topology x cross y. So this is the norm of x plus the norm of t of x. So in particular, this implies that the norm of t of x is less or equal than the norm of s times the norm of x. So, but this is finite. This is a finite number. So something that we saw a couple of classes ago. So if we have this expression for t of x, that we have that the norm of t of x is less or equal than a number times the modulus of x, this implies that t is a bounded linear operator from x to y. Okay, so maybe this was a little confusing and we have to look at it a bit again. But the point is, now we have x and y Banach spaces and we have a linear mapping. So this linear mapping is bounded, so here, it is bounded if and only if the graph of this linear mapping is closed. Okay, so what we have assumed is that this graph is closed, and we have shown that t has to be bounded. Okay, so the only thing that we used within this proof is not that t of x is bounded. Okay, so this is, we are not using bounded. We are not using boundedness of t. So we are not using continuity of T, but we are only using the linear structure to be able to say that G of T is a Banach space. So using the linear structure, we can say that it's a Banach space, and then we can take the projection and realize that this projection is a bijective continuous function. So then if we have a bijective continuous function, we have an inverse, which is going from x to G of T. Now the norm of this inverse controls the norm of T of x. And this is what we're saying here. Okay, and so this is a quick application of the open mapping theorem, which tells you that there are different ways of characterizing continuity for these operators. Okay, so next class we'll keep looking at some other things that come out of the open mapping theorem.